called soil. You'll get a soil test number come back, which is described as being soil organic carbon. And it's actually not really organic matter. Organic carbon is about 58%. Organic matter is about 58% carbon. And what's measured is, in fact, the organic carbon concentration in the soil. And that's then multiplied to give by 1.5 or whatever it is to give you a organic matter content. Now, it's not always correct, that upscaling, because as we'll see in a moment, not all carbon is equal in the soil. There's also inorganic carbon in the soil, and that's things like carbonates, which are quite common in anywhere there's limestone in the soil. That's calcium carbonate, and that's another form of carbon. When you get your soil test done, it's the procedure that's done in that soil testing is to remove the carbonate before the organic carbon is measured. So that's an important aspect, is that sometimes the labs, if they haven't done that correctly, might give you an artificially high organic carbon level because there's some inorganic carbon there. When we talk about carbon in the soil, we often talk about carbon stocks, and that's different to the percentage. And carbon stocks is the quantity. Soil organic carbon, organic matter are measured as percentages. Carbon stock is measured in tonnes, and it's the percentage of the carbon, so the organic carbon concentration multiplied by the density of the soil and how deep it is. In the carbon trading scheme, you have to measure soil bulk density, and the carbon stocks are measured in the top three 10 centimetre layers, 0 to 10, 10 to 20, 20 to 30, and they're measured and assessed separately as part of the assessment of a carbon stock. So, for example, if we're at 1.5% organic carbon, 1.5% organic carbon in the top 10 with a bulk density of 1.3, which would be a pretty normal one, that soil has a carbon stock of about 20 tonnes of carbon. But wait, there's more. It's not, when we talk about carbon stocks, when it's traded on the basis of the global warming percentage or potential. And the trading figure for carbon is carbon dioxide equivalence. We'll work out why that's equivalence in a moment, but CO2 equivalent is the unit traded, and it's the unit discussed in the carbon markets. And CO2 is 27% carbon. So 20 tonnes of carbon is in fact 73 tonnes of carbon dioxide equivalent. And that's the trading, if you like, that's the carbon capital in that soil at 1.5% organic carbon in the top 10 centimetres. The reason we go through that convoluted process is because the Australian Carbon Credit Unit is 1 tonne of carbon dioxide equivalent. It's also important when you look at figures about carbon in the systems, and that you're clear about whether they're talking about carbon percentages, carbon stocks, the amount, the percentage, or the carbon dioxide equivalent, because they all obviously, 1.5 is quite different to 20 is quite different to 73. So just getting that terminology is really pretty important straight up. So there's a question in the chat. Is there, Catherine?
No, I've just put typed a message for those who missed my start to say to use the chat function. So
okay, right, thank you.
I'll yell out when there is. That's
the question. So yep, come in any time with the chat there. I can see everything that's going on, I hope. So that's the carbon world. And when we sort of go and look at some of the issues about carbon and transfers and flows, etc., we talk about stocks and flows in the global carbon cycle. I know this is a bit esoteric to you. It may be a bit esoteric to you, but in fact, this is the basis of which we have to understand what's going on when we think about carbon trading. There are two things. The stocks are how much carbon, in this case, gigatons of carbon dioxide. So that's equivalent, gigatons of carbon dioxide, not carbon. So if you're looking at, say the carbon that was in plants or the carbon in the soil, that would be about, 27% of that number. And when you look on the graph or whatever it is, you have to understand whether it's gigatons of carbon or gigatons of CO2. And gigaton is just a billion tons of carbon equivalent. So the reason we use gigatons is because billion means different things to different people. If you're an American, a billion is 1,000 million. Traditionally, a billion was a million, not 1,000 million. So those billionaires in the US really aren't quite as rich as they thought they were. So in terms of the stocks, how much carbon is there? There's a whole bunch of carbon present in coal reserves, and we won't particularly worry about that. In vegetation, there's about 1,600 gigatons of carbon in those, and there's about 3 times more carbon in the soil than there is in plants. And in the air, there's about 2,700 gigatons. So again, that's about, if you look at it, that's almost half. Soil has about twice as much carbon as in the air. But the oceans have a whole lot of carbon dissolved in them, present as sediments. And it's about 136,000 gigatons of carbon dissolved. And that's the sort of size of the banks. But what's important to understand with what's happening with the carbon cycle is the fluxes or the flows, what's happening in and out of those pools. So in terms of carbon being emitted, our fossil fuel burning is emitting somewhere around 335 gigatons of carbon dioxide per year. Land use changes, so that's land clearing, etc., is emitting about 4 gigatons. Plants, our good friends, the plants, are absorbing about 11 gigatons of material. And the oceans are absorbing about 10 gigatons. And so that what we see in terms of that balance is that we've got about 19 gigatons of carbon increasing each year in the atmosphere. And, to get things in perspective, that's, they're the sort of numbers. 80% of terrestrial carbon's in the soil, and 60% of that terrestrial carbon is inorganic carbon dioxide equivalents. So that's the size of the pool. That's what's going in and out. And the consequences, what are some of the other pools? You might have, people say, well, in terms of those fluxes, what about things like volcanoes and bushfires? These are the estimates from volcanoes. So Mount St. Helens, which erupted in the US, I think it was in the 80s, emitted 0.6 megatons of carbon dioxide equivalent. And in fact, most volcanoes seem to have a net cooling effect due to dust that it throws up in the air. The 2021 bushfires in Australia, the estimate from the research that's been done on that says that they emitted 750 megatons of carbon dioxide equivalent, a million tons of carbon dioxide equivalent. And when we put that in perspective, in terms of Australia's emissions, total emissions, it's about 620 million tons of carbon. So in fact, the 2021 bushfires emitted more carbon than we would have emitted. And that normally emit in a year. And that carbon doesn't actually, that carbon in the bushfires doesn't go into our carbon accounting system. Globally, there's about 59 or 60 gigatons of carbon, of greenhouse gas, not carbon dioxide, but greenhouse gas that's emitted into the air. And we'll talk about what's the difference between greenhouse gas and carbon dioxide. But basically, 75% of greenhouse gases is due to carbon dioxide from fossil fuels. And that the production of those is that sort of triangulates back to the previous slide where we talked about how much was actually being emitted from fossil fuels. So the consequence, which everybody knows and reads about, is that those fluxes mean that carbon dioxide in the air, it's going up at 19 gigatons per year, means it's going up. And the graph on the top left is the measurement at Mauna Loa, which is on the big island in Hawaii. It's one of the Earth observatory networks, and it measures carbon dioxide concentration in the air. The red line there is actually the day, every week it measures it. It actually measures every day, but it gives a monthly, weekly averages. And the black line is the trend. And that's basically going up at about 0.8 parts per million a year. And that's a pretty steep rate rise. The red line goes in and out because of, mainly because of forests on the Northern Hemisphere. In the winter, they stop taking carbon dioxide in, and in the summer, they take more carbon dioxide in, so that sort of the lungs of the earth, the forests breathe in and breathe out, breathe in during the summer and breathe out during the winter. And that's why it fluctuates, by 7 or 10 parts per million. The bottom picture on the bottom right is actually the longer term trend. And, in the olden days when I went to school and we heard about plants growing, they were growing in 320 parts per million carbon dioxide. Now they're growing in 412 parts per million carbon dioxide. And it's that carbon dioxide that drives plant growth. It's the material that the plants take in photosynthesis and use that carbon to store energy for us and for themselves. So it's the energy in the carbon bonds that's released when we respire. We breathe out carbon dioxide. The plants breathe in, take in carbon dioxide, and fix that energy that they take from photosynthesis into those plants. So this is all happening at a pretty rapid rate. As I mentioned, it's not just carbon dioxide. Carbon dioxide is one of a whole raft of greenhouse gases, and in terms of, we talk about them in terms of their global warming potential. And if we take carbon dioxide, because it's the largest one, is given as one. Methane, which is derived from mostly from enteric fermentation, that is from ruminants, belching, etc. That methane has about 24 times the global warming potential of carbon dioxide, and nitrous oxide, which is produced often through soil nitrogen transformations, has about 300 times the carbon dioxide equivalents. They're called greenhouse gases, or ozone's there. It depends where it is in the atmosphere. It's right up in the top of the atmosphere. It's good because it stops UV radiation coming in. But if it's down the bottom and breaks down, it's not so good because it's quite reactive. They're called greenhouse gases and this is an issue of physics. There's nothing to do with policy here. This is an issue of physics, because what happens is when radiation, infrared radiation from the sun comes in, solar energy, those gases vibrate and capture some of the energy. And that infrared heat, some escapes to space, most is contained in the atmosphere. And that's why we're here, because we've had that warming atmosphere. But the consequence of that is if we, with more greenhouse gases, we end up with more heat being contained in the atmosphere, more energy in the atmosphere. And so the bottom right is the global trend in surface temperatures over the past 140 years. And again, going back to when I was a lad, you know, we're 1.2 to 1.3 degrees warmer on average than we were back in the 50s. And that all triangulates again back to the amounts of carbon dioxide equivalents that we've put into the atmosphere. So that's the sort of big picture. So what can you do about it? Well, you can sit there and worry about it, but there are some international frameworks. The first was the UNFCCC, United Nations Framework on Climate Change, which was, you know, we've been trying to do something for 30 years now, established in 1992. And in 97, they had a series of COP meetings, which were just the meeting of partners who signed into that first climate change agreement. And the sort of big significant trips along that journey over the COP values is that the first real one was the Kyoto Protocol, and you've probably heard that, which was really, they just said, oh, we're going to do something. We need to stabilise and reduce greenhouse gas. Okay, that was a good idea. They said that in 97, and it came into force in 2005. So the governments that signed on to Kyoto agreed to monitor what was happening to greenhouse gas production in their country and report on it every 4 years back to the UN. 2015, the Paris Agreement, COP22, was established, and what was agreed there was, okay, we're measuring it, but what are we going to do about it? And the agreement there was to try and to reduce emissions to get global warming less than 1.5 to 2 degrees by 2050, and that was the target that was set in the countries that agreed to the Paris Agreement, of which Australia was one of those parties, and the US. Not every country is part of that Paris Agreement, but most, particularly the less developed countries, but certainly we are Annex 1 parties to that agreement. So we're bound into that international agreement. The most recent one, COP21, which our Prime Minister went to, was what was known as the Climate Pact. And what that said was, okay, we're going to reduce emissions. We're going to tell you how we're going to do it. And we've got a target for 2050, but we need a target for 2030. It's like saying, I'm going to drive from Melbourne to Sydney in a day, but I'm not going to tell you where I'll be at lunchtime, because I don't really know. So you have to set that intermediate target as you move towards 2050. In that context, it's all a bit esoteric maybe. In that context, what's the view from Canberra? Well, I don't know what it'll be. I'm not sure what it's going to be in 10 weeks' time, but at the moment, and based on those agreements that we're in, Australia's position is that it updated its determined contribution from Paris with Angus Taylor and our good friend Prime Minister Morrison. They said that they would reduce emissions by 5% compared to 2000 to 2020, and that by 2020 they would have abated, that means reduced carbon emissions by 4 million tonne, and that they agreed that they would get to net zero, that is, that the carbon emissions would equal the carbon claims, carbon acquisitions, by 2050. But they didn't say, and they wouldn't commit to what their target was, other than saying that, yes, we will reduce emissions by 35%. There are some policy initiatives which were about how to do that. Things like climate resilience, 2 billion for climate resilience and adaptation, 21 billion over the next 8 years for next generation low emission technologies. And the one that plays into what we do, which is the carbon credits emission reduction fund, the carbon farming initiative, all those words. Carbon farm initiative was the first piece of legislation, and that set up a process where you could, the government would buy carbon credits off you to offset against our emissions to get that figure down. So what's happened since 1990? These are the sort of pictures we see. These are in carbon dioxide equivalents. In 1990, our emissions were about 630 megatons of carbon dioxide equivalent. By 2006, 2005, they'd gone down and come back up to 660. The most recent valuation, most recent audit is about 494. So certainly over the duration, Australia has reduced its emissions significantly. But let's just say that there's a bit of smoke and mirrors involved in that, because it depends when you take your base from. If you took your base from 1995, probably wouldn't look quite so good. The government's decided it would take its base from 2005, which is when the highest values were. There was also a dip down globally in 2021 because of that thing that happened called the pandemic. And certainly emissions in Australia dropped. As I said, globally emissions dropped by 5%, and Australia probably was certainly in that. And Australia also doesn't include land use changes, so land clearing, etc. So there is a bit of difference in the way that we can talk about it. But whatever it is, Australia's still got 1.3% of global emissions. So why would we even worry? Well, we're on a per capita basis, we're the highest carbon emitter, and our global emissions don't include the coal, gas or oil that we sell internationally there. If we sell coal to India, it's included in their emissions. And if we included that coal, oil or gas, would be 4% of emissions. So where do those emissions come from in Australia? Well, in terms of agriculture, it's about 13%, 14%. Most of it's from electricity and stationary engines, transport, etc. The fugitive emissions are emissions of gases, most often methane and carbon dioxide, particularly from coal and oil. So let's go on. It's now, we'll just mention that main policy area that pays into what we do in agriculture is the ERF, the Emissions Reduction Fund, and that's managed through the Carbon Energy Regulator, CER, all lots of acronyms there, of course. And it's the whole concept with the Emissions Reduction Fund is that the government would put some money in to buy carbon credits against which it could offset the emissions that were occurring in the economy. So it started in 2014-15 with a 300 million. And what is set by that carbon regulator is that it provides rules. How do you do that? How do you make purchases? how do you administer it? In that period, there's been nearly 1,200 projects registered, a quarter of them in agriculture, and nearly half of them in vegetation management. And the graphic on the right is taken from the government website that the CER has, the ERF has. And you can see that in terms of million tonnes of carbon equivalents, vegetation is by far the major strategy that has gone into the ERF. So that's where the most tonnes of carbon have been bid for with replanting and revegetation. Agriculture comes in a couple of ways. It comes in through soil. It also comes in through other areas such as managing livestock feeds. There's a small area for reducing nitrogen inputs to cotton. And the bid there is for 15 million tonne. So you can see that it's the big ticket item is vegetation, but in terms of us in soil and soil carbon, that 15 million tonnes of abatement is significant. That's what's been bid for, that 209, but in fact, there's at the minute, up until 2022-23, there's been 76 million tonne of these units delivered. So only a third of the credits have been delivered and signed off and finished. The government, in its most recent budget papers, the current estimates for purchasing these is 2 billion. That's in the forward estimates, that'll be down to 1.3 billion. So the budget is not going to be big to buy more and more of these carbon credits. And there's other ways you can do about it. Go about other than just selling them to the government. There are other carbon markets, but this is one carbon market that you can trade in. So there's actually an auction that finished yesterday, which was the 14th auction in the system. I haven't got the results for that, but the last auction in October, the government purchased 6.8 million tonnes of carbon dioxide in 24 projects, all vegetation and agriculture, and the value that was paid in that auction was nearly $17 a tonne of carbon dioxide equivalent. So that sounds like a big amount when we talk. What do we have? 70 tonnes of carbon dioxide equivalent in our soil. At $16, that sounds pretty good. So I'm not putting this up as a political issue, but one of the headlines in the last few weeks identified that Australia, in terms of its climate action, is ranked 171st out of 171 countries. And in its reporting back, and this is the graphic that comes out of the UN framework on carbon, and it rates Australia's overall policy rating as highly insufficient. It looks at what the trends were. Here we are today, 2020, and what is the 2030 targets? And the 2030 targets, they say, are insufficient, and the policies to get to those targets are insufficient. That's based on any pathway. And the other aspect is our fair share. And what that means is richer countries should do more than poorer countries. And Australia is part of the G20, so it's in the 20 richest countries. And it's not doing its fair share in terms of reaching the targets that they agreed to for 2030, and therefore the targets for 2050. So that's all in the public domain. The global opinion isn't very favourable. Guterres at the UN gave a bit of a bath to our policy initiatives, which was probably warranted. So that's the view from Canberra and the view from the UN and the view from the globe. What's the view from our tractor? If we're looking backwards, looking back, what's happened? Where are we with carbon? What's it all about? So when we talk about carbon, we're talking about soil organic matter. What's soil organic matter do? Well, what's it there for? Well, it's there as a source of nutrients, for example. It's not just carbon. Organic matter isn't just carbon. It's got nitrogen, phosphorus, sulfur, also, and micronutrients in it. A lot of copper and zinc are held in those organic materials. And it also provides some water holding capacity. It's able to hold water, not a great deal, but it certainly assists with holding water. It acts as a binder, gluing together some of the soil mineral particles. And it also provides exchange sites. What that means is it has negative charges on it, which can hold cations like calcium, magnesium, and potassium onto the exchange site and hold them ready for plant to exchange with plants. It also provides what things called chelates, which can mobilise things like zinc and iron and manganese in the soil. And it also stabilises the soil against erosion. And that's because of that binding issue, the way the soils are bound together. So in essence, it does a lot of things. Does a lot of things in the soil. Most importantly, I think it provides resilience. That is, if you just had a hydroponic farming system with sand as your basis, without organic materials in it, you'd be relying on every input and every removal of water and nutrients to be there, and you'd had no capacity to hold any of those materials. And that's where organic matter in the soil provides that resilience and the stability in the soil. So what is it though? Organic matter is lots of different things. If you look at organic matter, it's living organisms, roots and macro and microorganisms. It's partially decomposed plants, and that area there, partially decomposed plants, comes from the microorganisms as they die, which comes from the roots, and the other pools here, the particulate, which we'll talk about in a minute, are also in exchange. The three most common pools that we talk about are recalcitrant organic materials, particulate organic materials, and humus organic materials. And they're all based on size. Recalcitrant organic materials are often charcoal in the soil. And there can be quite a lot of charcoal in soils, particularly in our region in the Wimmera, where we're on old grasslands that were burned, and there is maybe 20% of the organic carbon that comes out is actually recalcitrant, and that's effectively non-reactive. The two other pools, particulate and humus organic carbon, are in flux with each other. And when we measure organic carbon, we actually measure all those three pools. And understanding this pool here isn't particularly reactive. It's actually the other pools, these two pools here, that are the more reactive ones. So what's the importance of these? This is an example of the organic carbon and the fractionation of the organic carbon into those different pools for a long-term trial, which is at Longerenong, run by Professor Roger Armstrong and the Department of Agriculture, and it fractionates those into recalcitrant organic carbon, particulate organic carbon, so big, smaller, and the smallest ones are the humus organic carbon. And the particulate organic carbon, this grey bit here, is labile. It's very active. That's a thing that really fluctuates quite a lot. And it's also got quite a high carbon to nitrogen ratio. No, that's important to understand. And then there's the humus fraction, which has got a carbon to nitrogen ratio of about 10. And that's really an important part, the biggest part. And it's also a little bit resistant, a little bit stable. So we've got a labile fraction that changes in and out and a resistant fraction. The inert fraction, this bottom, maybe 0.1%, 0.2%, doesn't really change. And as I said, it's a feature of fire-managed grasslands, which is typical of the Wimmera Plains, for example, which were burned over many, many centuries. That profile changes as you go to place, and so that land use and location affects the carbon stocks. I'm going back to carbon stocks, and we're talking about carbon stocks in carbon, not carbon equivalent. This is the language. We need to get this language right, eh? So if we're at Hamilton and looked at what the carbon stocks in that soil were in terms of particulate, humus, and recalcitrant, there would be somewhere around 50 tons of carbon, about half and half particulate and humus. So that soil has a very strong capacity to provide turnover of organic materials. If we went to South Australia, soils in Hart and South Australia, which is a crop system, much less organic material and much less particulate and humus. And as you go from place to place with pastures, a mixed rotation, you can see the proportions of those humus in particular changes quite significantly, and the amount and also the proportions. And that's important to understand, because if we go into thinking about how we manage those carbon pools, we actually need to understand a bit more about the size of those pools and how quickly things move through it, as we mentioned at the start with fluxes and pools and fluxes. The amount of carbon you can store in a soil really depends on the environment that you're operating in. The best place to store carbon is in a swamp, in a cold, wet place, like Ireland, for example, where they have peat bogs, or in Australia, down at the Kuirop swamp. They're places where carbon enters the system from plants, but it's too wet and too cold for it to be oxidised back. Whereas when we go to something like a desert, for a start, everything's water limited. There's not much plant growth. And so the input and the potential storage in deserts and semi-deserts is low. If we go to croplands, again, we've got a potential to store, but it's certainly less than, say, forests, temperate forests or boreal forests. So we need to, that sort of sets a view about carbon storage is actually a function of the environment, and it's also a function of the way the water and temperature operates. And that gets reflected. This map here is a map of soil carbon concentrations across Australia, across the eastern seaboard and into southwest and Western Australia. And it pretty much, those carbon contents pretty much reflect the rainfall trend as we go inland. If you threw a set of isohyets on those, you would pretty much run across So if you set the ISO heights to where we are at, 400 mil, most of the places that have got 400 mil rainfall have between 0.1 to 0.75 soil carbon, soil organic carbon. So you get higher rainfall, you get higher soil carbon, and so on until you get down to the very wet places that might have greater than 4% organic carbon. So that carbon is a consequence, firstly, of the environment and the soils, but it also can be managed within the context of those environments. And the next graph here is probably the one that we see and think about most in terms of managing carbon. This graph came from a trial at the Waite Agricultural Research Institute in South Australia, and it was a permanent rotation set over 75 years. And for the first 34 or 33 years, the soil, the field was in a wheat fallow rotation. So cultivated wheat fallow rotation, stubble removed, cultivation, plant, cropped plant, etc., planted crop, etc. The blue line is what happened to the carbon, organic carbon, in that period. So it went from 28 over 30 years down to 15. So it virtually halved in that period. But more significantly, if we looked at the fractions, the humus carbon went down, and the labile fraction, the bit that we really turn over quickly, effectively disappeared and just bumped along a little bit along the bottom line over the years when it was cropping. So after 30 or so years, it was decided, okay, let's we've seen what's happened there. Let's turn this back into a permanent pasture. And what happens to the carbon? Well, the soil carbon, total organic carbon, went back up to about 20. So it didn't actually get back up to 28, but it got up to 20. So the benefit there of that 30 years of pasture was about 5 tonne of carbon. And over the period, that humus went up, and the particulate carbon went up. But again, it didn't quite get back up. Neither of them got back up to where they were. So these fractions here are the resilience that I talk about. When you've got this level of particulate organic carbon, you're really running on a quarter of a tank of fuel. So you can get by, but you just can't go very far or very fast. So once you get a bit more carbon in the tank, you've got more options. So I think that's an important concept to have in your mind, that as pastures and cropping, traditional wheat fallow cropping was pretty exploitative of that carbon, and putting pasture does help get back. So the question we ask when we think about what we're going to do with carbon and carbon trading is, how much carbon can we get? How much carbon can we add into the soil? The soil carbon stock or content is a result of three things. Firstly, the capacity of the soil to hold carbon, how much we put in, how much we take out. So if you think about that as a bucket, carbon inputs coming in, carbon losses going out. The carbon inputs are from the plants that are growing there, the tops and the roots. The carbon losses are erosion, as product removal when we take grain or meat away, and also as microbial respiration, as the bugs in the soil capture and use some of the carbon. Now, this is a super simplified way of looking at it, but it serves a purpose for thinking about our issue of how much carbon can we capture and use. So if we looked at a plant material, looked at a virgin soil in the Wimmera grey clay on the Wimmera plains, that would In terms of carbon, that would have about 2.2% organic carbon. We know we've measured those. We did some surveys of roadsides and uncleared land, such as up at the Barrett Forest, for example, halfway between Horsham and Warwick Nabil, and the sorts of values we get are 2.2%. Now, the reason that's 2.2%, not 5% or 3%, is again because of the climate. In that situation, we don't have erosion, we don't have product loss. All that's happening is a cycling of carbon around. If the climate's warmer, we get more growth, more carbon input. We also get more respiration. If it's a colder climate, we get less growth, less carbon input, less respiration. So that turnover there is pretty much in balance with what's coming in and what's being respired out over the years. And it can't get much higher than that simply because if there's more carbon goes in, the bugs start to metabolize it. So if we looked at how big that bucket across Australia, well, in fact, most of Australia has a pretty empty bucket. It has a very small bucket, and that bucket's full. It can't really hold much more carbon. And that's one of the issues in the carbon farming initiative is where do you direct your energies? It's obviously to places where you can get the most amount of carbon. And that's a consequence of how drained the bucket is and how big the bucket is. So that comes into clearing history, crops or pastures, how much clay is present. And you can see where we are here, there's actually quite a good potential for carbon capture. We do have a capacity to store carbon. Other places, such as on the Darling Downs also, and Kingaroy, etc., has a good capacity. Western New South Wales, far western New South Wales has virtually no capacity. But then the western slopes of New South Wales do have some capacity. So if we think about that idea, here we are in the Wimmera, where our typical soils here are 1.1% carbon. We're 2.2, 1.1 now. You guys on the farms would know exactly what that is, but might be down to 0.8. So in terms of that bucket, the bucket was 2.2 or 28 tonne. We're now down to 14 tonnes. So in theory, we've got 14 tonnes to fill that bucket up with. So how would we do that? Well, with in our farming system, let's say we're growing a wheat crop, 3-tonne wheat crop, that'll produce about 6 tonne of stubble and another tonne of roots or so. That material is about 45% carbon. So we do take the roots, we do take the wheat away. So that's quite a lot of carbon disappears with that. But that 6 tonne of stubble and tonne of roots has about 3 tonne of carbon in it, which gets tipped into the bucket. And we'd think that now, if we started off with 14 tonne of carbon, we've now got 17 tonne of carbon. And is that what happens? Is that 17 tonne now really appear? If we keep doing that, say after 15 years, and we keep adding 3 tonne of carbon, do we have 60 tonne of carbon present? Does the soil carbon content go to 3.6% with 60 tonne of carbon stocks? Well, sounds too good to be true, doesn't it? In fact, we do know what would happen. We had, in association with Incitec Pivot, we had a long-term experiment at Darlin, just the first silo west of Horsham. And we looked at different fertiliser programs over 15 years. And the bottom story of this graphic is that in 1996, when the experiment started, the carbon levels in the field was 1.1. So we had a carbon stock of 14 tonne in the top 10. I'm just talking the top 10. By 2011, 15 years later, the carbon stocks where we had added phosphorus had gone up 0.2%. So they'd gone up from 1.1 to 1.3. The carbon stock had gone up from 14 to 16.5. So yes, it increased. And that rate was 0.17 tonnes of carbon sequestered, is the word, per year. So if we go back there to that picture, we had 1.1. We're now at 1.3 in the soil. We're at 16.5. Why aren't we at 3.6? Well, the simple reason is there seems to be 33 tonne of carbon missing. And where that 33 tonne of carbon is, it's being used and respired, turned back into carbon dioxide by the soil biology. And that's the consequence of living in an environment that has warm, moist soils for a lot of the period of time. The microbes there do, in fact, respire and take that carbon. 90% of that carbon ends up being re-respired, and we can only store a small amount. And that system there is actually virtually the strategy that we have about adding carbon, full stop. That experiment was continuous cropped, zero till. It had permanent cover, that is, the stubble's crop residues weren't removed. It didn't have a cover crop, but it had crop residues left there. We burnt the field once because of resistant ryegrass in 15 years, but it never had never had a cultivation or anything like that, other than the cultivation and seeding. And we also didn't just grow wheat; we grew a normal rotation of canola, wheat, barley, and a legume, so 4-year rotation, and that was done fairly flexibly. So, that they become the standard strategies that we would think about, and they're the three core principles of conservation agriculture anyway. And the consequence of those is following those will put carbon into the soil, but the rate at which it puts it in is not that quick. So this is an example of some work that one of my colleagues at Melbourne University did. What he looked at was these graphs are the soil depth, 0 to 10, 10 to 20, etc. What was the effect of the different management practices on the percentage increase in carbon in those depths due to conservation tillage, the use of pastures, residue retention, and nitrogen application. And where did that occur? So most of the benefit for conservation tillage increase occurred in the surface, residue retention in the surface and a little bit deeper, pasture in the surface and nitrogen fertiliser in the surface. So there were benefits. There's definitely those strategies did improve soil carbon, but in terms of how much they did, how big was that improvement? Well, we said from the Darlin site it was 170 kilograms of carbon per hectare per year. This analysis says that it had about 140 per hectare per year for conservation tillage from the experiments that they looked at. Pasture 140, residue retention about 60, and 40, 50 from nitrogen. These figures aren't necessarily additive, so you can't just add conservation tillage, residue retention, and fertiliser application and get 2.5, 250 kilograms. In fact, they do in some ways. They're not necessarily additive; they're complementary. So that, yes, we can add carbon. In terms of our environment here, it's probably looking at somewhere around 150 to 200 kilograms of carbon per hectare per year is what we could sequester. And in fact, that falls in pretty much in line with some work that was done out of CSIRO by Jeff Baldock, looking at across Australia, what's the capacity. We saw how big the bucket was. The two graphs here are what's the input and what's the losses. And so if you look at the size of the bucket, the amount that goes in, the amount that comes out due to erosion and respiration, we still end up with an area in the Wimmera Mallee and on the York Peninsula in South Australia of having a reasonable capacity to add carbon. So that's the good news. The bad news is that it's going to take a long time to add some. And, to add 170 kilograms, 150 kilograms per hectare per year is going to take a long time to build carbon up. So is that a problem? Well, if you want to build soil carbon, yes, it is, because each year you're only going to accumulate up until a maximum, until you fill the bucket up, about 7 tonne of carbon dioxide equivalents each ACC. There's too many C's in that ACC unit. But what we're doing is, you have to realise that part of our farming system is actually not to build carbon, but to use it. And we use organic materials for all those purposes I mentioned at the start, but we also use them as a source of nutrients and a sink for nutrients. Organic matter has a pretty consistent nutrient density. So 100 units of carbon is about 8 of nitrogen, 2 of phosphorus, and 1.5 of sulfur. That's a pretty consistent number. So if you have 14 tonne of carbon in the soil, which was our 1.1%, that has 800 kilos of nitrogen, 200 kilos of phosphorus, and 140 kilos of sulfur. So the nutrient content of 1 tonne of soil carbon is 57 kilos of nitrogen, 14 kilos of phosphorus, 10 kilos of sulfur. And you probably see where I'm going with this, that the dollar value of that nutrients in that 1 tonne of carbon is 150 nitrogen, given $3 a kilo for nitrogen, maybe $7 for phosphorus at the moment. Who knows what it'll be tomorrow. So each tonne of carbon has a nutrient value of about $240. That's pretty significant. So we actually use those nutrients and cycle them in and out. We remove some carbon, we release some nutrient. If we want to replace some of the carbon, we'd also have to supply the nitrogen, the phosphorus, and the sulfur in about those numbers. And that becomes, there's been a bit of research looking at fertilizing to improve soil carbon. And certainly when you apply fertilizers to meet the soil microbial demand, you can build soil carbon, but it costs quite a lot of money to do that. So it would cost you $240 a hectare to build that tonne of soil carbon back up. So with understanding that, you're all still with me? Anybody still there? Don't know. You've all gone home, have they? You put your hand up if you like.
Still here. Are there any questions for Rob so far?
It's either perfectly clear or perfectly unclear, isn't it?
We'll find out. No questions. We'll keep moving on.
So that was the view looking backwards from the tractor. What about the people outside the tractor? What are they thinking about this carbon business, if you like? What are they seeing and thinking about? Well, they see opportunities where farmers can build soil carbon, that we can trade it, that we can have a carbon market, we can buy and sell carbon. There's a mechanism for it with the ERF. There's a whole range of opportunities to do that. In agriculture, the main ones, as I said, are soil carbon and revegetation. As I mentioned, there's also things like cattle management, dietary supplements for beef and dairy, and nitrogen fertilizers on cotton. All those have protocols which you can look at in terms of how much carbon you could accumulate and sell that credit to the government, who then offsets it against our carbon emissions. There are lots of other areas that qualify too. It's not just agriculture. So, for example, energy consumption, making more efficient generators, changing coal-fired power plants to hydro or to wind power, waste where you might capture methane emissions from rubbish dumps, transport, changing transport from coal to gas or to electric, and so on. There's also just recently been an announcement that carbon capture and storage would also qualify. And that's a process where virtually you've got a big machine that sucks the carbon out of the air and puts it underground. We also have those things. They're called plants, and they suck the carbon out of the air and put it under the ground, and they actually do it without much assistance. So the question we come to then is, in terms of those opportunities, can you just go out and plant some trees, use zero till, go stubble retention, and sell that carbon stored to the government? Could you do that? Of course, it sounds too good to be true, doesn't it? When you sit back on the tractor and look forward as you're going along, what can we see ahead of us? So looking at carbon credits, what do you have to do? If you're looking to store carbon in your grazing or cropping system or in perennial woody horticulture, that might be forestry, etc., there are three principles that have to be seen, that have to be met. And they are, firstly, you have to do something new and additional to what you've already been doing. So if you've been stubble retained zero till for 10 years, you have to do something different, additional to what you were doing. And that's the principle of additionality. The second principle is you must measure it. And that means with soil carbon, for example, the process is you apply for a soil carbon as bid for a soil carbon project, and you take soil samples each 5 years to verify what the soil carbon increases are. If there's decreases, you have to give some money back. So it's verifiable, additionality and verifiable. And it has to be, for carbon, it has to be permanent. And permanence in Australia under the ERF is 25 years. It has to be stored for at least 25 years after the first credits are issued. So those three things, additionality, verifiable, and permanence, are the fundamental principles that go into storing carbon credits and selling carbon credits. So let's have an example. Say you go in and you sample, you decide you're going to do this. You're willing to get a plan about it. You're happy to change what you're doing, and I don't know how you'd change if you were a farmer who was burning stubble and in a crop fallow situation. You might plan to go into direct drilling. That plan has to be agreed to or developed with a qualified contractor, one of your friendly agronomists, and also people specifically who have that business of doing the verification. You develop a land management plan. In this case, plan was to increase organic carbon by 0.5% over the first 5 years and retain that for another 20 years. So that was to provide 6 tonnes of carbon stocks, 22.5 Australian carbon credit units. So that's the potential. You said they are $16. So $16 by 20 is what, $300? That sounds pretty good. But when you do that, there's a few discounts that need to be applied. Firstly, to achieve that, to do that increase in carbon, you're going to have to use some greenhouse gases anyway, so you have to discount that. There's 5% taken off that 6.2 because of measurement uncertainties. There's 25% discounted because it's a long-term contract, and 50% deferred from sampling periods for the first 5 years. So in fact, when you discount that 22 carbon units, you end up with 4.5. And that 4.5 at say $18 is 84. And of course you pay a broker's fee, 25%. So that your net benefit over 5 years is $63 a hectare. And it's taxable. But the good news is you don't have to pay GST on it. So that's the process, that's the outcome of looking at increasing carbon content by 0.5% or 6 tonne of carbon. Value of $63 over 5 years, $12 a hectare per year. And those projects, there's lots of them. Most of those projects aren't done by individual farmers. They're usually done by aggregators. Aggregators are registered with ASIC. It's considered as a financial product. It's not as an environmental product. And what an aggregator does is they're the ones that negotiate with the clean energy regulator who buys and sells the credits. And they'll put together a bunch of projects and amalgamate them into a formal single contract, each reported separately. But in some cases, it might be a large organisation. Nap Station, for example, has contracted 70,000 tonne of carbon equivalents over 30,000 hectares, over their 30,000 hectares, as their most recent, that's a very recent contract that they've gone into. They did that individually, but most projects we would be involved in would go through an aggregator. And the projects would be using this. A lot of them might be soil carbon projects or reforestation projects, etc. So that's where you now lose a little bit of control in the way you manage this, because it has to go into a bigger pool. And the aggregator takes, let's say 25% or whatever is 20% of that credit. It's worth having a look at a recent publication in The Conversation by Rich Eckhart, who's at Melbourne University, and Peter Grace, who's at Queensland University of Technology, both of them carbon experts. and there's eight other carbon experts, and they reviewed a scheme. I won't name the place or the where it is or who it is. That there was a proposed credit project from a US broker for an Australian farm, large Australian farm, and the company who was doing the crediting collected data by satellite imagery and did a little bit of soil sampling, and their suggestion was that they could store 7,000 tonne of carbon in 1 year over 1,000 hectares by pasture management. That is, increment a carbon credit of 7 tonnes of carbon per hectare per year. And that sort of doesn't triangulate very well with where we would saw the figures of maybe 0.2 tonne of carbon per hectare per year. So this example that Rich goes through really makes us think about the methods and making sure that what we're getting into is realistic, because these guys have got into selling 7,600 tonne of carbon, but they may get paid for that, but if they can't do it, they've got to give all the money back. And in terms of that being a carbon credit for Australia, that actually doesn't accrue in Australia. It goes on the US carbon budget. So it's actually no particular benefits of an offset to Australia. So it's really worth looking at that article and seeing some of the ins and outs of the system. The other thing to realise is that those guys are bound into something. They're bound into a 25-year contract, and any net loss along the path, remember you're sampling every 5 years, every 5 years you might have to add or take out money to balance that sampling error. So it's not quite as simple as getting the money and sitting back with land. If that land's sold, that ACC has to be bought out, or the new owner agrees to continue doing what you were doing. It might be difficult too if you've done a plantation and somebody wants to clear that. If you've done a big tree planting and that is then decided that you'll clear that, you have to give back. You have to buy out those units, those carbon units. And in a cropping situation, where you've gone zero till, it might mean you can't go in and do a strategic tillage for weeds. It might theoretically, if you looked at the carbon effects of liming, that also could be taken in as a negative, because when you put lime on soil, you actually produce carbon dioxide. So, the things, those contracts bind you into a whole lot of things that you need to think through pretty carefully. With your advisors and with the aggregators and with everybody involved in the farm. So where does that leave us? Well, yeah, you can certainly increase soil carbon, soil organic matter. It's slow, and a bit like everything in life, it's slow build up, it declines rapidly. As soon as you switch back from conservation cropping to cultivation, that labile pool will disappear very quickly. So we also know, yes, you can increase it, and yes, it has a value. If you think of the value in the nutrients associated with the carbon, it's $250 per tonne. The value of an ACCU is $18 per tonne, locked for 25 years. The international price is a lot higher. There's a significant demand for carbon credits, for carbon purchasing. The EU price at the moment is about $140 Australian for a tonne of carbon dioxide equivalent. So there is demand. How high that price? The price got up to $50 in Australia on the market. Not in the ACCU market was constrained to, I think, $12 or something below that. So that's where it leaves us. Yes, you can do it. Yes, it has a value. The value might go up. Will it go up to $250 a tonne for the nutrients? I'm not sure. So what I think is important is carbon credits, etc., are an option. They're a difficult beast to manage. In terms of your farm, I think you farm for good crops and pastures. That is, fertilisers, sow on time, etc. Good crops and pastures, because of the roots and the material they produce, build healthy soils. And it's the healthy soils that then build soil organic carbon. And it's the soil organic carbon that's built from that healthy soil that goes back and supports good crops and pastures. So the story for me is that you're much better off managing your soil, managing soil organic matter, soil organic carbon for your own benefit, and not necessarily trying to get into a carbon market and try and trade carbon commodities, because you're selling probably the best part of your farm. So with that, Catherine, let's see if anybody's still present and awake.
Thanks very much, Rob. I personally have learnt a lot during that session. I think it's going to take me all day and a couple more coffees to fully process it. But it was fantastic and you've timed it perfectly. So I feel like you might have been doing this for quite some time to get your time and your presentations down pat.
Thank you.
Are there any questions? Feel free to unmute yourself, put your camera on if you would like.
I'll stop sharing my screen if I can make this thing work properly.
Hello, am I online? It's Calvin Muller from Warwick-the-Beale.
Hi, Calvin.
Hello. I've got a comment, perhaps, or a question. How much can we increase our soil organic carbon by using or planting a crop of a dedicated green manure crop and leaving it on the surface by crimping?
If you do that number, Calvin, that we thought about, 5 tonne, 10 tonne of biomass, which is pretty good. If you leave it on the surface, it's still going to respire. The transformations, the respiration that the microbes are going to do are still going to turn over. And the numbers we found, we did some green manuring research in the olden days when I was at Longanong, and we really couldn't move carbon very much with green manuring. Even with a big, like a vetch crop of 5 to 7 tonnes, green manured or brown manured even. Brown manure is a little less damaging because you don't necessarily have the cultivation of a green manuring ploughing it in. But it is, in terms of the percent, you'd be lucky to move it 0.1 if you could measure it. And that's one of the issues with any of these measurements of the values, because they fluctuate so much during the year because of whether the microbes are working or not. It can be a variation of the measurement that you're looking for can be within your measure of uncertainty. So the numbers, another example, we did some experiments at Longanong where we were using piggery litter from the piggery sheds over at Gree in towards St Arnaud. We put on 50 tonne per hectare of piggery litter and thought this will be great. This will really pick up the soil carbon. But what we didn't do was use a conservation farming system after that. And after 2 years, we couldn't remeasure any of that carbon that we'd applied because we'd gone through 2 crop cycles with cultivation. So it's not just what you add, it's how you manage it as well.
Could I make a further comment? I did green manuring 33, 34 and 35 years ago, and I'm still getting quite a benefit with the crop yield with no urea.
Yep, absolutely. And that's a lot to do with the nitrogen fixation, which is a consequence of the legumes you're using. And the other benefit you do get is, of course, weed control, strategic weed control, difficult to control weeds. And the nitrogen benefit's important. The weed control benefit's important. The nitrogen benefit comes from the fixation and the organic materials in the roots, of course. You can measure nitrogen much more accurately than you can measure carbon, funnily enough, simply because carbon fluctuates. So, yeah, I agree. That's a very important part of the farming system, is green manuring. But, you know, there's no silver bullets to this. It's all part of a system view.
Thanks, Rob. I agree with you about the weed control. We've had to use very low inputs of herbicide to control weeds. Thanks, Rob. Very interesting talk.
Thanks, Calvin.
Thanks, Calvin. Were there any other questions from the group? No, thank you very much for coming along and listening this morning. We do have a short 5-question survey that when you do leave the meeting, it should hopefully pop up on your screen. So if you could please provide some feedback on today. I've also left a space if there are any other topics, soil related or otherwise, that you would like to see a workshop in, please let us know. We can definitely tailor workshops to the Wimmera region. We have a lot of experts in the region that we can tap into as well. Thank you very much to the Catchment Management Authority again for partnering with us today. They're an apology due to a staff member's funeral this afternoon. So yes, this will be, the recording will be available on their YouTube channel, and we'll send that around as well so everyone can have a look back if they'd like to watch it again in their own time. Thank you so much, Rob. That was wonderful and so much detail. And for me, not being in the carbon space very much, just I learned a lot as well, and I hope everyone else did too and enjoyed the session. Thank you very much, and
Thanks.
Have a great rest of the day.
Thanks, Catherine. Just remember you are 18% carbon yourself, so you are in the carbon space, and we're all in the carbon space with every breath we make. So thank you. Thanks for the opportunity. And I did go into a lot of detail because I thought it was important to contextualise what we were doing. So thank you. Thanks all for listening.
Absolutely. Thank you.